Fantastic. Well, thanks everybody for joining us today. Today we're very lucky to have Torsten Hansen joining us from the University of Aarhus. A quick introduction to Torsten. He's in the final year of his PhD program at the Department of Geoscience at Aarhus University. His project concerns the structural evolution of primarily the Cretaceous units in the Danish Central Graben. Torsten has a BSc in Geoscience and an MSc in Geology, both from Aarhus University in Denmark. And during his studies, he has been a visiting researcher and done courses at the University of Victoria in Canada, the University Centre in Svalbard, and most recently with the Geomodels Research Group at the University of Barcelona, which I think we'll be getting some results of today. So without further ado, I will hand over to Torsten. Take it away, sir.
Thank you very much, and thank you so much for inviting me. I'm very honored. Now let me just see if I can find out how to share my screen again and kick off the presentation. Do you see a slide in presentation mode now?
Yes, we can see that.
Yep, perfect.
Oh, that's great. Let me just find a pointer here. All right, yes. So I'm gonna talk about the salt-related kinematics of basin inversion with some perspectives from first of all the Danish North Sea, mostly from seismic data, and well, only from seismic data, and also some brand new analog models that I have been working on at the University of Barcelona with Oriol Ferrer. And the other two people here, Ole and Katrina, are my two supervisors here in Aarhus. So yeah, here's the outline for what I'm gonna tell you about. I'm gonna get the acknowledgements out of the way in a moment, and then I'm gonna talk about. I'm gonna give you a brief introduction to inversion, basin inversion, and the basin inversion that happened in the late Cretaceous and Cenozoic in the northwestern European region, so around the North Sea. Then I'm going to zoom into the Danish Central Graben and show you results from our 2021 paper. And after that, I'm going to talk about analog sandbox models of inverted rift basins. We're going to end off with some key points, and hopefully there'll be some time for questions after that. Yes, I forgot that in the end that I had that animation, but that's the sandbox model, and we'll get back to that in a bit. So yeah, I told you who my supervisors were. This the PhD project I'm doing is funded by DTU offshore near Copenhagen at the Danish Technical University, and it's part of a research project on the tight reservoir development, focusing on the low Cretaceous reservoir rocks in the Danish North Sea. The Danish Underground Consortium, which consists of Total Energies, the Nordsø Fund, and Noreco, provided seismic data and gave me permission to show it. I use software for seismic interpretation and modeling, and that was provided by Ellis, Schlumberger, and Petroleum Experts, respectively. If you see some nice color maps from seismic data that I have in these slides, the color maps were designed by Fabio Cremeri, and they are freely available at the address here. And all right, basin inversion. So what is that? Basically, when we talk about inversion in tectonics, we're basically talking about a switch in tectonic mode. And with basin inversion, and more specifically positive basin inversion, we're usually referring to the reversal of subsidence in an extensional basin due to tectonic shortening. And there's been presented various definitions, shorter or longer, throughout the years. But I think this is probably the most simple one. And basin inversion usually involves the at least relative uplift of former rift epicenters, as the rift basin is basically being squeezed out of its place. So you see a figure here on the right from Yamada and Maclay, really nice cartoon showing firstly a rift half-graben with wedging synrift deposits here, synrift units. If you subsequently squeeze that whole thing, insert horizontal shortening, you'll see that you get this folding, anticlinal folding and uplift of the rift epicenter here, and that's usually that shortening is usually accommodated by folding, as I mentioned, but also fault inversion. So the initial normal fault here gets a smaller or a larger reverse component, and that may help accommodate shortening and the squeezing out of this rift basin. A key thing you'll come across in the topic of basin inversion is that it's not mechanically feasible really to move steep normal faults in a reverse sense, because they are steep, and reverse faults, as you probably all know, they prefer a more shallow dipping surface of failure or a slip. So for that reason, this the folding, the buttress folding we often see in the upper hanging walls of inverted basins is a normal component, and often the first thing you recognize in inverted basins. Also, you may create shortcut faults like the one you see here, the incipient football shortcut fault here, which during shortening provides further structural complexity. But the thing about these uplifted buttress anticlines is that they provide four-way dip closures, and often that in a lot of places, and certainly in a few oil and gas fields in the Danish Central Graben area, those are important reservoirs that are being produced. So understanding basin inversion has great relevance for resource exploration and productions, and also, for instance, subsurface storage, also in the years to come. At least I hope so. Yeah. So we had a quite important phase of basin inversion in northwest Europe during the late Cretaceous and Paleogene, even into Miocene times. You see a map with the UK, Denmark, Norway, and so on, and a series of extensional basins that were Mesozoic extensional basins that were subsequently inverted. With hatched yellow, it's marked the late Cretaceous inverted basins, and with red the younger Paleogene inverted basins further to the west. And you'll see here that this corresponds the orientation of these fault-bound inverted basins. It makes very good sense that they would invert during a north-northeast directed shortening, as was the case when Africa, Iberia, and Europe started to converge around 90 million years ago. Well, yeah, it's probably around 30 years ago that in the classic papers by Ziegler, the cause for this inversion was mainly thought to be the alpine orogeny, but we know now that inversion actually initiated before the alpine orogeny did, while we still had oceanic lithosphere between the converging plates. So it's an interesting example of the effect of the effect that far field stresses can have on weak zones in the lithosphere. And of course, the reason these zones are weak is because they were rifted in the first place. Interestingly enough, here, if you start out in the northeast, for instance, up here in the Egersund Basin, offshore Norway, you'll see only a tiny bit of shortening recorded in these basins here, and a tiny bit of uplift along the master fault here. As you move further southwest, you cross the Danish Central Graben, and you might end up down here, at the Saltpit Basin, or the broad 14s Basin offshore Netherlands. And these basins saw a lot more inversion, so much relative uplift that erosion dug down into the late Jurassic syn rift deposits. The great thing about our study area in the Danish Central Graben here is that this area saw mild to maybe moderate inversion in some places, meaning that the magnitude of shortening was small compared to the initial magnitude of extension. That means that we have the extensional geometries nicely preserved. They're easy to delineate, yet we still have so much inversion that it's still a good area to enjoy inversion structures. At the same time, the uplift was so limited that erosion was not significant. So we have very nicely preserved syn inversion deposits, and those are great if you want to date specifically the timing of inversion phases, which was done in the Danish Central Graben around 20-30 years ago, even more. And actually since then, before we came along, no one had really done dedicated studies on basin inversion in this area. And that leads me on to the material from my first paper from last year, which is about the structural styles of inversion in the Danish Central Graben, surprise, and the interaction with mainly the sextine, so the upper Permian salt. You see a structural map with Cretaceous structures outlined. The sector border for the Danish area goes around the part of the Central Graben like this. It's sort of a pointy nose. And down here you see that we're right in the center of the current North Sea area. The biggest structure here is the master rift fault that goes all the way down through the Danish sector here, with the crystalline basement on its northeastern side, the Ringkøbing Fyn High, and to the southwest, the rift basin complex. And in these hatched areas, you see the extent of late Cretaceous and Paleogene basin inversion in this area. And I put in here an isochore map, thickness map of the chalk group, the Upper Cretaceous Andanian chalk group, which is more or less sin inversion. And you'll notice here that the bright areas here, where the chalk is relatively thin, corresponds very nicely to the areas that saw relative uplift during tectonic shortening in the late Cretaceous. All right. Also, the inverted zone here, first of all, it mimics very nicely the late Jurassic rift epicenters, which means, of course, that where we saw the most inversion-related uplift is also where we saw the most rift-related subsidence, which was accommodated on especially the master fault, the coffee soil fault. I love that name. And I'm gonna show you. I'm only gonna show you three sections from this area, which are marked here, and I have mapped along with the sections, so don't worry about getting lost. The great thing about this study area here. Oh, and I should have said that. Yeah, we actually have great 3D seismic data covering most of the Danish Central Graben, but in order to make ends meet, I chose to cut out around somewhere between half and 2/3 of this area to concentrate on the area that saw the most inversion. Still, this smaller area is great because Danish Central Graben basically straddles the structural high between the northern Permian Basin, with a lot of textile salt to the north, and the southern Permian Basin to the south. So if you walk through the Danish Central Graben along the deepest part of the rift basin, following the base of the coffee soil fault, which is outlined here along the edge of the study area, you'll see that if you come from the south, you'll be first in an area with gigantic and very attractive mobile salt structures, pillows, diapirs, delaminating salt wings, stuff like that. When you move further north, the salt, or at least the mobile amounts of salt pinch out, and you'll only find pockets of thicker salt, which is mostly probably somewhere around, yeah, I should be able to read that, maybe between 100 or 200 meters max in the central part of the study area here. In the very northern part, we meet thick salt again. So this is a great area to study the influence of varying amounts of deep salt below the sin rift units. And what initially inspired me to work on the connection between inversion and salt was that I came across the paper by Duffy and colleagues from 2013, where they studied the influence of textile salt on rift basin development in exactly this very area, using more or less the same seismic data as I did, and that led this very beautiful conceptual sketch of developing rift basins with various amounts of salt. So then I thought, yeah, they almost didn't mention the effect of inversion. So I thought, oh, I should have a look at that, because yeah, that's in Danish we say it was like the ball right in front of my right leg, but it was a great opportunity, basically. So the study was set up in a manner like this. I wanted to know about the structural control of salt during inversion. Basically, we had 3D seismic data, which was fairly well constrained, at least in the more shallow levels, with borehole data. So I mapped surfaces and structures. I constructed thickness maps, structural maps, fault maps, and folds, salt structures. And also I considered seismic stratigraphic relationships. In order to investigate the kinematic relationships between one subsalt basement structures, and that would be on this very simplified stratigraphic chart, will be down here in the lower Permian or even older. Number 2, salt layers and salt structures. That's mainly the upper Permian textile salt, which is basically all halite in when you find it in this study area. Also, we have these secondary thin evaporite units in the Triassic, the red halite and the Muschelkalk halite, which are more or less only 1 or 2 wavelengths on the seismic data. But as you will see, they have something to say as well. And lastly, how these elements, how they are related to the inversion structures and the syn inversion geometries we see in the late Cretaceous and Danian. So the short group up here, which is also the main where you find the largest number of at least the classic oil and gas field reservoirs in the Danish area. So let's start off with this section here, which goes down through the central part of the study area. Here we basically have some salt. You'll see the major rift bounding master fault here, the coffee soil fault, segment number 2. And yeah, maybe there's a bit of salt here, not too much. But as we move southwest, we bump into this guy here, an inverted salt roller or anticline, if you will. And also as we move further up this slope in the basalt surface, we see we see a bit more salt before it pinches out. And let me just take you through the units here. It's very basic. So you'll see here in purple we have the Triassic to mid-Jurassic. We actually have some syn-rift units here, and that's because we had a number, something like 3 or maybe 4 individual rift phases during the Triassic and Jurassic. The upper Jurassic is shown in blue here, and that is when we have the rift climax. So that's where we find the most syn-rift deposits. And in the deeper parts here, where you have several kilometers of syn-rift deposit, it's mainly deep water, organic rich mudstones, shales, and the like. That's also where you find the main source rock in the area. I should say, and maybe even apologize for the vertical exaggeration of 3. It highly exaggerates the tip angles of structures and layers, but I felt it was a good idea at the time in order to highlight the syn-rift, the syn inversion stratigraphic pattern we see in the light green chalk group up here. You'll see we have the classic buttress fold geometry here, right above the upper tip of the coffee soil fault, with a displacement of the depth center from the hanging wall to the foot wall as an effect of inversion and uplift of the syn-rift deposits. The funny thing is then that if you move to the other margin of the rift basin, you also see quite prominent, at least for this area, inversion structures. The so-called Boyens Ridge. Yeah, they have terrible names. That's because they're named after all the wells, which again are named after old Danish folklore characters and the like. Yeah. Funny thing about these structures is that, yeah, they make sense at first. You look at, yeah, you have quite a bit of folding. Makes sense. We have a lot of soft, easily deformable shales here. We have a reverse reactivated normal fault down here. That, interestingly enough, salts out into the Permian fault. So these are thin-skinned or at least somewhat decoupled structures. This deformation was decoupled from the subsalt down below, and in the subsalt down below you find these old normal faults that have opposite dip polarity than the inverted faults up above. They all more or less have a north-south structural trend, struct direction, which you can also see out here. I've marked this is again the thickness map for the chalk group with thin inversion structures indicated. You have a trend of anticlines here. And you might also be able to see I've marked with this dashed red line the western margin of what I call significant inversion. You have a slight bit of folding out here during the late Cretaceous, but it's really not much. So that's quite interesting. Thin-skin structures to the west, verging to the southwest, and the classic thick-skinned buttress fold to the northeast along the master fault. Let's move north a bit. Here we basically have no salt, even though I did interpret a bit at the time. I wouldn't do that today. You don't see the lower part of the Triassic here. It's not as smooth as when you have a bit of salt to sort of provide a attachment. But this is also really interesting. You have this compared to before. You have more or less like a more narrow inversion zone here with a lot of folding that extends quite deep into the Cinerift deposits. And whereas at the same time, you have a bit of reverse reactivation on normal faults, but it's not a lot compared to the degree of folding. You still have this southwest verging inversion trend here, and this peak or anticline here is actually the northern continuation of one of the thin-skin structures from the section before. Also, you should notice even if you look at this section when it's not vertically exaggerated, you still have quite a considerable dip at the base of the Cinerift deposits here, because you had a lot of extension, a lot of normal movement on the coffee soil fault here during late Jurassic rifting. But interestingly enough, we don't see the classic buttress fold above the tip of the master fault here. There's a bit of something here, but it's only really when you move out here that you have a prominent monocline facing the northeast. Yeah, so these it's quite clear. This for the area, these units were squeezed quite a bit. Okay. Yeah, it's a bit uncertain what the subsalt fault geometries are like here, but in the end, I think they're not really that big. I think it's mostly what's going on in the rift infill. I think that's quite a bit of decoupling here, even though we don't have salt, and I will come back to that. Now let's go to the very south of the study area. Now we are this is beautiful. Obviously, we have a lot of salt here, at least relative to the other sections we just looked at. We have a prominent pillow here, and this is not even the where the pillow is the thickest, the Crocker pillow. We have delaminating allochthonous Permian salt here that is unzipping these Triassic salt units marked with yellow. And I shouldn't spend too much time on that structure, the Dan structure, because that's all everyone they only want to talk about Dan when they see this, and it's not really the point of my it's not really on my agenda here. I didn't spend too much. I didn't consider too much anything with this work, with a structural restoration or whatever. That wasn't my aim here. We have Permian salt plate along the coffee salt fault here. That's because it was also the faulting here only occurred after salt deposition. So salt was eroded on the footwall here, but has been preserved along the master fault here. A nice buttress fault here. And then to the west, even though we also have some inversion further west here, we see a very great looking little inversion structure here with a reactivated fault that attaches into the upper one of these Triassic halides. So that's quite structurally complex, and if you want to see a great example of a very similar structure without inversion, I can only point you to O'Sullivan and Childs, their work from which was published last year. That's Conor O'Sullivan and Conrad Childs from the Irish offshore, the Corrib structure, if I'm not mistaken. Yeah, here it's the inverted cotton of Corrib, the long lost inverted cotton of Corrib resides. Okay, so yeah, nice pattern. Again, thin-skinned structures to the southwest. Yeah, thick-skinned inversion to the northeast. You should notice here that now the base of the salt is really quite flat, whereas in the other two sections it was dipping quite steeply towards the larger basement faults. Instead, this inverted thin-skin fault here utilized the sloping Triassic Muschelkalk halide in the carapace of the salt pillow here. Very smart and very nice geometry. Okay, let's try to put this together in some sort of synthesis. Here you have a simplified sketch with in gray. You have the base salt, so yeah, the top of the subsalt. You have the coffee salt fault marked here, and also a prominent but deeply buried north-south striking rift fault here, the Gorm-Kyra fault, to be precise. And in pink, well, you'll see we have at least a small area here where probably we don't have any salt at all. If you go north or south, you'll gradually move into thicker Permian salt. Here it's so thin that it's not really mobile, but when you go further south, you'll meet mobile salt, although most of it has concentrated in these salt pillows and swells and walls, diapirs. It's actually called the salt dome province, this one here. To the right, you have the inversion structures, so mapped from the chalk group higher up, anticlines, monoclines, inverted faults, and younger inversion-related thrusts marked in white. You'll see there's a nice trend here that goes southeast, turns directly south, and also right atop the coffee soil fault, we also have some reverse movements during inversion. And here we have the sections again, basically to the northeast. I can't see the top of my own screen, but basically that's a very classic thick-skinned style of inversion, except for the northernmost section here, where the monocline verging northeast here is somehow been placed further into the basin. The interesting stuff, though, is along the southwestern and western margin of the inverted area, where we see that when we put the inversion structural trends on top of the salt structural trends, we see that they line up very, very nicely. There's a great correlation here, and it's really quite simple. It's because these salt structures seem to have localized thin-skinned faulting above already during rifting, and these thin-skinned faults were subsequently reverse reactivated during late Cretaceous shortening. All right, and also down here at the south end, we have this very nice trend of reverse reactivation above the salt pillow in this section, and you can follow it for quite a distance, or 20 kilometers or so here, where this thin-skin fault detaches into a sloping Triassic halite unit. Yes, we have this area up here where we basically have no salt, and I said, yeah, I think it's still formation inversion related deformation here in the cover unit are still decoupled from the subfault. And I think that's basically because not too far to the south, we have nicely salt attached inversion structures, and also to the northwest. And I think they were simply able to reach across this area with no salt, especially given that it's all soft. It's shales, maybe even with some considerable overpressure at the time, that allowed for the whole thing to be squashed together, and these thin-skinned structural trends could reach across this gap in the Sextine fault. Okay, kinematic models. I only went back to the end of rifting. This is basically this section I showed you with some salt, and yeah, it's a very nice, at least on the large scale, half graben geometry with the very large master fault here to the east, a buried basement fault here, and thin-skinned antithetically orientated detaching fault here to the west. Also, a small figure here for the Crocker case, with thin-skin faults detaching into Triassic faults. Then shortening occurred, and we saw reverse reactivation on the master fault, and also on these thin-skin faults here along the western margin of the rift basins. And that makes very good sense with sort of the widely accepted theories that yeah, salt structures are weaknesses that have a tendency to localize deformation during both during extension, rifting, and inversion. So that makes good sense, yeah. But then there's the thing: where did the corresponding deformation occur below the salt, in the subsalt? At least for the case of these thin-skin structures, how do we balance the first extension and then shortening we see in these thin-skinned structures with movements in the basement? And I basically already gave you the answer here, but I think I should just take a step back and let's go back in time to 1996, where Thomas and Coward basically described the same thing in the South Viking Graben, offshore Norway. I think at least we have a reverse reactivated master fault with in its hanging wall some Permian salt, a salt swell with a carapace and some bridging rift units here. And on the opposite side, we have these smaller faults that soil out along the fault. So they basically provided a very easy explanation. Oh yeah, we have these small antithetic basement or subsalt faults that were also reverse reactivated. They're just so small we can't resolve them on the seismic data. And I think even if they were correct, they would be right at least that these faults would probably not be resolvable. The thing is, though, it's not really satisfying, because also in great data like I am fortunate enough to have 3D data, very new, very beautiful. It's not really direct evidence of subsalt compressional deformation. So I kept asking myself, where is the shortening going on? Is it just distributed across the area, or is it localized somewhere? And I tend to think it's actually localized, given that, for instance, in this section here, we see that at least from here to here, there's a considerable, at least on the order of 500 meters or even more of relative uplift, if you take a regional at the going through here at the top rift units like this. So I don't think shortening is that. I don't think there was much shortening going on in the basement out here, at least. And then I stumbled upon an interesting paper by Stewart from 2014, which is about so-called triangle zones in extensional and in inverted basins. And I think I shouldn't spend too much time on this. It is quite nerdy, but basically the thing is, you have domino block rifting with a basal salt layer or a weak layer that gradually becomes deeper and steeper. Also, the master basement faults here become more and more shallow, which gives them more and more friction, and eventually the salt might provide a better pathway for a fault attachment than this fault surface here with a lot of friction, and that'll lead to the cover units here above the salt. They will start to roll down along the fault, creating a fault weld with a syncline like you see here, and the thick-skinned extension here will then be balanced by a thin-skinned antithetic fault up here. And when you start squeezing the whole thing, the blocks start rotating back up, and you basically get the opposite. So the triangle zone is this red area here, which might explain at least a bit of thin-skinned inversion here. And you see it here. So I think that this deeply buried basement fault here actually reactivated in a reverse sense during the late Cretaceous, and that shortening balances the shortening we see on these thin-skinned structures here, while at the same time, directly above the tip of this fault, we see no buttress folding whatsoever, and that's because this upper part of the fault was basically blocked by friction, and somehow the units here were accommodating the rotation and internal strain, and we got an effective detachment, even though the salt is rather thin here for these thin-skinned faults. I hope that makes at least a bit of sense. All right, so zooming out again, that means that, yeah, we could, assuming that shortening in the basement was actually concentrated along these larger basement faults, it would mean that we had reverse reactivation of the master fault here with corresponding buttress faults like this one in the cover above, while along the western margin we have thin-skinned inversion structures whose shortening is balanced by reverse movements on these deep basement faults here, even though we don't see a direct effect of inversion directly above them here. Yep. Okay, so that's not really a quick summary, is it? But yeah, salt distribution correlates along the western margin of the inverted zones in the study area. Salt distribution and structures correlate very nicely with the inversion structures above, because the salt structures simply they would be effective in localizing shortening during inversion to form these structures, thin-skinned structures above. We see that even thin salt layers like the Triassic halides and even apparent wells, like for instance down here, still provide effective detachments during inversion and probably also during extension. And lastly, a triangle zone in Census Stewart provides at least one explanation of where we might balance extension and shortening for related to thin-skinned structures in the basement below the salt. Okay, I'm using a lot of time on that, but now comes something completely not completely different, but yeah. It was very nice. I went to Barcelona for 3 months. I just came back recently, got to use my hands, push sand in a dark basement most of the time, which was great. And then you get something like this, which is just amazing, really. So, analog modeling, sandbox modeling of inverted rift basins with early synrift salt. And mind you, this is work in progress, so it's a bit rough around the edges right now. What's the motivation for doing something like this, using this methodology of sandbox modeling? Over the past several decades, at least back to the mid-80s or so, analog modeling has been an important tool for geologists researching rift basin development and subsequent inversion. At least according to Khan et al., this is a preprint of a very new review paper on analog modeling of basin inversion from solid earth, and it's freely available at the website if you are interested. Of course, it would be great if we could recreate these structures we see in the seismic data from the Danish Central Graben in a sandbox model involving a salt analog, so silicone, and also in that perspective. Yeah, we should. I had to come up with a better scientific question motivation, so I came up with this. I wonder what are the effects of variations in the distribution and geometry of early synrift salt. What's the effect on structural development of rift basin with continued extension and then subsequent inversion? What's the kinematic role of the salt here? And that's relevant to the Danish Central Graben again, because we have these. We have both areas with no salt, we have areas with some salt, and areas with a considerable amount of salt and salt structures. So especially the focus here was I was looking for what's the degree of coupling across the salt. Is it partial? Is it fully decoupled? Do we see full coupling in some places? How did salt migrate during inversion? And are there any particular effect of salt wells, and particularly fault wells, that might help us say something about how relevant these, for instance, the triangle zone model of Stewart are to natural examples? Oh yeah, I should mention here you have a couple of classics here, classic analog inversion models. This is by Buchanan and Maclay from '91. That's the year I was born. Yeah, so it's not that old, but yeah, they used a rigid footwall. That obviously gives you some limitations in that, for instance, you won't see any footwall shortcuts when you invert this thing here, because the footwall it's a piece of wood. Later on in 2017, sorry, Oriol Ferrer presented this again with rigid footwall blocks with various geometries to investigate the effect of pre-rift salt during inversion. I think it's pre-rift, maybe a bit of synrift. No, it's pre-rift. Yeah. Okay. So yeah, I thought initially, oh yeah, I'm going to use a rigid footwall. Also in the Danish Central Graben, the footwall at the coffee salt fault, it's granitic in most places, and we don't see any shortcut structures. But I was told by a smarter colleague that no, we should try something else. We should try something like what Dooley and Hudek did in their 2020 paper on basin inversion involving salt below the synrift deposits. And actually also, this is also early synrift salt. You have a section from one of their models here that had a considerable amount of shortening, more shortening than earlier extension. Then you get something like this. Here you have the extensional mini basin that subsided into the salt before being uplifted by inversion. I'm not going to get into too many details about the materials and scaling properties and the like, or things like that. But we're basically using colored quartz sand with specified parameters, for instance, grain size, range. Viscous silicone is the salt analog, has specified viscosity and everything. We also use viscous silicone like Dooley and Hudek at the very base below the pre-kinematic layers to sort of have a say in where basement faults develop when we start extending the model. Because we're using viscous silicone, we need to use moderate displacement rates, and that means we are using, for a model the size we have, we're using around 0.5 centimeter of extension or shortening per hour with pulsed extensional intervals. where we give the silicone time to flow and settle after we apply a new layer of sand, because then you'll have various, you'll have pressure gradients, and the silicone needs time to adjust to that. So we can have some nice salt structures. Here's our apparatus in Barcelona. It's all here. We have two end walls here that are both attached to worm screws that connect them to two motors. You only see one of the motors here. Along the sides we have glass walls, so you can. They give some friction, but you can get a good sense of what's going on in your model. And this is, mind you, this is a two-dimensional rig. It has a width of 35 centimeters, and that width is so that we assume that in the middle of this box we won't see any effects from the friction along the glass walls. The whole thing is 86 centimeters long. To attach to the end walls, we have two metal plates that in the middle are connected by a rubber sheet that we fastened with glue or tape to the metal plates. And this rubber sheet allows us to extend the box, and also to the rubber sheet will take up at least shortening an amount of shortening that is smaller than the initial extension. And this is something different from what Julie and Hudek did. They fastened, when after extending and stretching the rubber sheet, they would fasten the metal plates to the table below and unscrew them from the end wall here, and then start pushing the end wall towards the center of the model. We didn't want that much shortening after inversion related shortening, so we found out it worked actually quite well. The rubber sheet is able to take up the shortening very nicely. Okay. On top of the rubber sheet in the middle and overlapping with the metal plates, we put 4 millimeters of silicone, not the salt analog, but 4 millimeters below the pre-kinematic sand, in order to provide a detachment for basement faults. The thing is, then we would put this wedge-shaped, a so-called fault seed, on the middle of this silicone, and you got to be quick because it's a big blob of polymer silicone, and it'll start flowing fairly fast. So you need to cover it with sand, and that's one of the weaknesses of this method, is that it's really hard to make things exactly the same way as you did the last time you made a model, when you're trying to put down this piece of polymer silicone and it sticks to everything, and it's just horrible. But with a left sloping wedge of polymer silicone like this, we can expect to get left tipping basement faults that nucleate from the tip here in the middle of the sandbox. So that is, instead of using a rigid football block, we use this method instead, inspired by Julian Hudek. Okay, now we covered the silicone seed with sand. You have some blue and black layers here, and each layer is scraped to make it perfectly planar. And then we have these spotlights at a low angle, beaming light onto the sand, so we can see any topographic variations caused by faulting or folding very nicely in the surface. We have a camera somewhere up above taking orthophotos of the whole thing, and then we can use that for strain analysis with some kind of software later on. Also, this pre-kinematic package is almost 9 millimeters thick, and you can more or less say then 1 centimeter in this model corresponds around 1 kilometer in real life in nature. That's fair to assume. Okay, I can see I'm using a lot of time. I will go through the phases quite fast, and I will show you the nice stuff after that. Basically, we did a bit of rifting with the sand here. So we got these two graben, graben A and graben B. Graben B nucleated at the polymer seed. Graben A is sort of a side effect that nucleated at the edge of the polymer layer, the basal polymer layer here. Okay, nothing to do about that. We filled this topography with salt analog. So again, polymer, silicone, same thing, until we got these thicknesses. So above the structural highs, around 3 millimeters, up to 12 millimeters in the deepest parts of the graben areas. So that is our early sand-rift salt. On top of that, when it was flat, we put a thin carapace, magenta colored, and started even more extension rifting. You see the effects of that here, coupled faulting in the beginning at least. And then eventually we get upslope diapies on the slope here of graben A, and sometimes they would pour out so much silicone I would have to cut away a bit. But we continued extension, filling in sand into these areas with regular intervals and leaving the polymer time to settle, adjust to the pressure, until we ended up with 72 millimeters of extension after putting down the polymer. So that's around 99 millimeters of extension in total, almost 10 centimeters. Then we started squeezing the whole thing. So we started inversion. Inversion, luckily enough, it fits with the current theories. It rejuvenated the salt diapies here. We saw a lot of silicone pouring out during inversion because, yeah, the graben here is being squeezed. And above the half graben here, above the polymer seed, we saw so much uplift that we actually did some erosion into the deeper layers, even though we would lift the regional levels, so the scraper 3 millimeters with regular intervals. So we shortened the box 50 millimeters in total, so basically half as much shortening as earlier extension. That gave us these sections here. So we preserved the model with water and gelatin and cut it in slices afterwards. I'm going to zoom into two specific areas here, the graben A, where we have salt diapies, and also graben B above the silicone seed here, where we saw a lot of relative uplift. Yes, and the reason the sand looks terrible here is because there was some air trapped, and unfortunately water wasn't able to penetrate the area here. It was trapped by the salt analog and hence not very well preserved. Zooming in to graben A, we have a very nice series of structures here. Basically, it's a half graben with nicely synclinal sand-rift deposits here. Note that we don't have anything that looks like, or we don't really have direct signs of shortening in the subsalt here. Certainly no reverse reactivation of the master fault here. And that's one of the drawbacks of sandbox modeling, is that the so-called faults we develop in sand, they are only a tad bit weaker than the sand around, the unfaulted sand. So we don't really see any, it's hard to reactivate these structures in sandbox models. Okay, here's a list of interesting things. Yes, so no clear evidence of shortening in the subsalt units, but we have some primary welds here and here. We even have at least a bit of fault welding here, which seems to have been related to these really steep reverse faults that actually developed during rifting. Again, very peculiar, but quite common phenomenon in extensional basins. We have at least constricted diapir. It's not completely decapitated, at least not in this section here. And we have, interestingly enough, the suprasalt units were tilted to the right during inversion, as you can see from the yellow and green layers here. So not really, if you were to reverse reactivate the basement fault here, you would expect the whole block to rotate to the left, but we see something else. And generally also when we look at the inversion structure here, we see a left verging thrust, which it's not really, it's not directly connected to, certainly not reverse reactivation on the master fault here. So it must be coming from somewhere else to the right. We move to the right to the smaller rift basin above the silicone seed. Here we see a bit of subsalt shortening, and I think it's quite funny how, even though we have 5 centimeters of post-rift shortening, this is basically the only direct evidence of shortening in the subsalt layers. So yeah, that's a football shortcut. We have again a primary weld. We have a bit of fault welding, I think. We have some syn-rift salt inflation here, very nice. And now we have the suprasalt units were tilted the other way to the left. So maybe that indicates that, yeah, we had at least to some degree reverse reactivation of at least the fault trend here, because we use a silicone seed. So that's quite a good result, I think. I think it's mostly right verging to the right, an anticlinal inversion structure here. So a different patterns than in the other graben. Okay, so putting that together, we see decoupling of the formation above and below the silicone in these graben where we had thick or relatively thick early syn-rift salt silicone. We see, yeah, I'll put myself out there and say we saw mainly antithetic inversion uplift in the graben here, certainly here, and synthetic, so inversion structures that tip the same way as the basement fault, as the subsalt fault below here. The left verging shortening here it's very likely balanced by shortening over here in the subsalt here. So I think that points in a very good direction, that using this polymer, this silicone seed here, actually makes us able to more realistically model inversion than when we don't have sort of a ramp for reverse reactivation at depth. Comparing to the seismic, we see, I was very happy to see this, to the right, we have rotation of the layers above the salt. Yeah, towards the left, we see the same thing in this section here. In the graben over here, graben A, they rotated at least slightly the other way. Same thing we see in our seismic example from the Central Graben here. So that's just nice. Then we also did a non-inverted rift basin model that I couldn't resist showing you, and now we're getting close to the end here. The thing that happened here is that I did what I would call an improvement to the aperture, the setup before starting this model, but that turned out that eventually meant that the seeded, where we have the polymer seed here, this half graben fault just went crazy, and just we saw a lot of subsidence here, where before it was the graben here at the edge of the polymer that took up the most subsidence. So much extension on the half graben fault here that eventually we actually connected the salt analog with the basal polymer, which is not great at all. It doesn't seem to have affected the structures here too much, so we can still enjoy the section here. We have, I'm going to zoom in to this portion here. We have, oh yeah, this is for review number 2 from my paper from last year. Yes, silicone or salt did actually move upslope during rifting. I was right. And okay, I didn't mark the features, but we have nice crestal collapse fault below the salt on the rollover fault here in the hanging wall of the half graben. We have some small, very cute salt rollers up here, thin skin structures, verging, tipping, detaching into the sloping silicone here, a prominent up dip salt inflation, and a footwall, small footwall salt anticline right here. Yeah, that's what tells me that silicon moved upslope, that we have this inflation here. So yeah, I would really like to invert this thing here, but that'll be for another time. All right, key points to round it all off. In the Danish Central Graben from seismic data, we see that salt distribution and salt structures apparently had a considerable influence on inversion kinematics, at least along the western margin of the inverted basin, where antithetic thin skin faults developed, detaching into the salt. We did some analog sandbox models. They seem to tell us that models of inverted rift basins with early syn-rift salt, we can imitate with our models quite important aspects of the structure. We can imitate structural styles that we observe in the seismic data from our study area in the North Sea. So it seems that analog models, despite inherent flaws, like it's very difficult to reactivate existing faults in sand, you can still provide important perspectives on, for instance, basin inversion. Yeah, they have provided important perspectives for the last few decades, and they will probably continue to do so in the years to come. All right, that's it for now. Thank you very much. I hope you were able to stay awake, and if you have some questions, I will be very happy to answer them. Here's a list of references that I didn't manage to finish. If you have any, if you want any references or anything particular from this stuff, I'll just get in touch, and my contact details are here, and I will see what I can do. All right.
Great. Thank you very much, Torsten. Yeah, really nice work. Very nice models. That was great to see. I think we covered a lot of ground there. So we do have some questions in the Q&A if we've got time and you're not too tired from all that talking already.
Yeah.
Right, let's start then. So we had quite an early question in the chat from Salim Shaker. How do you compare the exploration success on Bo Jens Ridge to the other structural features, if any? It's quite.
The thing about the funny thing is that the particular field that the research project I'm part of concern is the Valdemar field, which is located in the Boyens Ridge. The Valdemar field is not, the reservoir is not located in Upper Cretaceous rocks. It's located in Lower Cretaceous carbonates that are much more tight due to a higher content of shale, sorry, of clay minerals. There's oil, and it's a few wells are producing quite well. So that was also a reason to start a research project to try to find out how can we actually make this even more profitable, because it seems that it's got something to do with the depositional phases and also the natural fractures you find in the crest of this inverted structure. And interestingly enough, we see extensional faults, small extensional faults at the very crest of the structure that seem to have affected the reservoir here. So I think it's I guess in the end it's not a very successful reservoir, but it's successful enough that it's worth looking further into.
Right, great. Okay, so then we've got two questions from Piotr. First one is Triassic salt autochthonous, i.e. deposited in Triassic times without any influence of zechstein evaporites? Or maybe there was a bit of extrusion of the zechstein salt in Triassic time, so it could be regarded as redeposited zechstein salt.
Ooh, that sounds quite technical, but yeah, we're dealing with Dan, of course. Everyone wants to talk about Dan, and I don't know much about Dan. It seems to me, and yeah, you should get in touch with Ole, my supervisor, because he's worked on the Triassic quite a bit. He's a bit hard to get a hold on, though. But maybe one day. The thing is, my feeling is that I don't think there was ever that much Triassic salt deposited, so my feeling at least is that it's definitely a allochthonous Permian salt. Whether about the timing of extrusion, I don't really know, but yeah, certainly that's what I know a few guys in Barcelona who would be very happy to discuss that with you. I haven't looked at it really, unfortunately.
Yeah, interesting questions about the origin of that. But the second part of Piotr's question was then how and when intrusion of the salt within the Triassic section visible on one of your profiles has been formed. So I guess that also comes back to what you were saying about not having looked at this structure in detail.
Yeah, I don't have a good question to that, but I think it would be you might assume that the lamination took place during certain tectonic phases where we saw abundant rifting or also inversion. Funnily enough, we do see there was a growing anticline above the Dan structure here during the late Cretaceous. So I think it's very likely that at least the structure was squeezed during inversion. But it is very interesting, this topic. Maybe I hope to do more work on that one day, maybe.
Yeah, it looks like some might have been squeezed out during that inversion event. Okay. So then there's another question from Celine that's a bit abstract, but do you think salt buoyancy had any impact on the uplift and shortening, or just lateral stress only?
Oh, that's a good question. I haven't thought about that. My initial thought is that we had, in this section, we have quite a bit of salt, but in large parts of the study area here, the salt is not that thick. So I think it was mainly an effective player. If you will, it was mainly working as a detachment horizon for faults.
Yeah, above. I think it would be difficult for salt to have any buoyancy effect in a situation like this. I think it's
definitely
it's a very
that's certainly a thing I learned by doing analog models, is that it's very easy to choke salt movements if you pour on a lot of sand from the beginning when you start extensions, for instance. So it needs time to get going.
Right. Okay, and then yeah, there's a few more questions in the chat to go. So we have another question from Rasmus Stenhoj. Did you by any chance locate gas-saturated faults through the whole chalk group in the Salt Dome province? Gas-saturated faults.
Yeah, Rasmus.
Yeah.
I think you're having a go at me here. Did you by any chance locate gas-saturated faults through the whole chalk group in the Salt Dome province? Ooh,
I guess in
I have no idea. I guess not. But it is quite interesting. A thing that a guy called Florian Schmidt, who's working at the Geological Survey in Copenhagen, he's worked quite a bit on the chalk group and published some stuff where he argues that there was a lot of fluid escape taking place at the same time as inversion. And those features indicating like giant pockmarks, stuff like that, they are often situated right above fault zones. So I think it's very likely that we have, at least at some point, there was gas saturated faults in the chalk group.
But you didn't see any pockmarks above any of these faults in your data set then?
Oh yeah, it's the same data set. It's all over. I see. Okay. I'm not an expert, but I see features that I suspect are something like ancient mud volcanoes or something. Yeah, I know it's carbonates, but
so there is a lot of fluid movement in this area.
There's certainly a lot of weird stuff, and that was basically the premise for Florian's own PhD on the chalk group. He had to investigate funny-looking things in the chalk group.
Okay, that sounds like a fun PhD. Just investigate funny-looking things. Okay, we have a question from Frank Peel. Is it possible that there is an underlying Paleozoic rift underneath the region, and that these Paleozoic rifts don't have a one-to-one match to the Mesozoic rift faults? That is what we see in the East Irish Sea Basin of the UK, and it gives rise to some interesting geometries, which you can't understand just by looking at the Mesozoic rifts. This might help explain why the geometry of the inversion structures seen at the top blue interval appears to be incompatible with simple inversion of the subsalt Mesozoic rift faults.
That is a very good point. And I think, yes, I think there are definitely deeper structural trends that have some form of influence on the more shallow features we see. I don't think, I certainly haven't looked too much into it, but I know there was a PhD, I think, at our department at some time. He looked into that. And there's some very, very deep Devonian or Carboniferous deposits, especially in the western part of the Danish Central Graben. So definitely, there's definitely something to consider there, and I haven't. But
that would be interesting to look into. Yeah, there's always older structures that have a sneaky influence.
Yeah.
Okay, so moving on, I have a question from Gonzalo Calvo. Is strike slip or oblique slip inversion considered in modeling regions such as the North Sea?
That's a very good question, I think, because all the old classic papers from the late 80s, and also a guy called Ole Weibeck, who was the first to specifically study in detail the inversion structures in the Danish North Sea here. They initially interpreted, and I think I still have my pointer here. I'm just taking the questions away here. So, for instance, the trend here, the western margin of the inverted zones here, the so-called Arne Ridge here, that transitions into the Boyens Ridge here, they were initially interpreted as flower structures. And it was back when it was right after the what's the name, the paper on flower structures came out, and I guess it was all the rage. I think we the thing is, there's not a lot of small scale features that indicate, for instance, at chalk group levels, that you had there's no like oblique faults or small things that would indicate a considerable amount of strike slip. It's very likely that shortening was not perfectly perpendicular to the rift bounding master fault in this area. But a funny thing is, in the crest of the Bo-Jens Ridge, the north-south anticline here, we do see northeast-southwest, small northeast-southwest striking normal fault, and that fits quite well with a north-northeast, south-southwest directed shortening that reactivated a north-south lineament, I think, in that you would get this a bit of, can you call it wrenching, along a north-south lineament during shortening, but it's mainly dip slip movements, and I think that's a more simple explanation than introducing a lot of strike slip. But strike slip certainly has a long tradition. There's a long tradition of interpreting strike slip structures in the North Sea, and I don't know if it's completely irrelevant, but yeah, good question.
Yeah, there's probably some component of that there. Okay, so the next question from Constant. Yeah, I think this may be the last question actually, or I'll double check the chat afterwards, but otherwise this is the last one. Thank you for a very interesting talk. Is there any effect of 3D salt movement along strike of the Danish Central Graben? Additional note, there is an example of reverse reactivation of normal faults in sandbox models by Konstantinovskaya et al. 2007 in Tectonophysics.
All right, thank you for letting me know. I need to get more into the literature on analog modeling. Yes, there are indications that salt was. Let me just find the salt thickness maps real quick. So as it looks now, we have mobile salt structures in the very south of our study area and in the very north. There are indications, and that was first introduced by Duffy et al. In 2013, that larger amounts of salt were initially present along the northern margin of where we see sort of a salt pinch out in modern days. And certainly right here, you can see that, especially in the early Cretaceous, when rifting had more or less ceased, at least for most parts, there was a considerable southward migration of salt into these surrounding salt structures, which caused a very circular area of subsidence without any fault to explain the subsidence around it. So yeah, I think, and also I think that's the case to the north, that because the area in the middle here is basically where the rift basin is the deepest, where you have the most rift-related subsidence in the late Jurassic. So I think it's quite a natural thing to expect that salt would have somehow traveled up slope along fault systems, away from the heavy load of rift deposits here, to areas with a more thin overburden.
Yeah. Okay, yeah, great. I think that was our final question. Hopefully that answered the question. Obviously, there's a lot of interesting things that we could discuss within this region, and hopefully the models are helping to address some of those questions. So yeah, thank you very much, Torsten. This was a particularly long session. Thank you to everyone who has stuck with it this far. I'm happy that at least some people stayed for the ride. I was actually aiming for a short presentation, but I guess
wasn't
there's just
meant to be.
too much. Yeah, there's just too much interesting stuff here to keep it to a short presentation. But yeah, thank you very much. This will be recorded, so anyone who missed it can always catch up on YouTube. Otherwise, thank you very much, and we'll see you for the next Salt Basins webinar. Thank you, everyone. Thank you, Torsten. Goodbye.
Thank you. Bye-bye.